Okay, we're going to do example problem 1 on page 261. I'll read the problem. It says a large chunk of ice with a mass of 15 kilograms falls from a roof 8 meters above the ground. A, ignoring air resistance, find the kinetic energy of the ice when it reaches the ground. And B, what is the speed of the ice when it reaches the ground? Now you could use kinematics to solve for the velocity at the bottom, but I just want you to see here that you could also use energy to find the velocity just before it hits the ground. And the key here is this. So here's what's given. This ice is going to fall down 8 meters, and it's got 15 kilograms. We want to know what is the kinetic energy at the bottom and what is the velocity at the bottom, right as it squishes this person. Now, kinetic energy. Mechanical energy. This is the initial mechanical energy. The mechanical energy when the ice is up here. Now, mechanical energy is defined to be kinetic energy plus potential energy. And that will be equal to the final kinetic energy plus the final gravitational potential energy. Kinetic plus potential will equal kinetic plus potential. Remember that the mechanical energy, by definition, is the sum of the kinetic energy plus the potential energy. Remember that? Now, look at this ice at the beginning. Does it have any kinetic energy? No, it's released from rest. So it has no energy due to motion because it's not moving. So this is 0. Now look at the end, just before the ice hits the ground. Yes, it is moving. Does it have any height? It has no height. So therefore, the final gravitational potential energy will be 0. That means all of my initial gravitational energy will turn into kinetic energy. Well, how much initial potential energy does it have? Well, that's going to be mg plus its initial height. And what is kinetic energy? Well, it's 1/2 the mass times the velocity squared. But remember, actually it asks for this. It asks for what is K final. Well, that's equal to K final. So K final, the final kinetic energy, is equal to the initial potential energy, which is mgh. And what is m? What is g? What is h? And now all we have to do is multiply all that out. So the final kinetic energy will be what? Well, if you do all that, I think you get 1,180 joules. If you round it off. Is that right?
Yep.
Now that's what it's asking for. I mean, if you read the problem, it's not asking for the speed yet. It's asking for the kinetic energy it has at the bottom. So this is all for part A. Now for part B, well, now I kind of started doing that right here. K final equals 1/2 mv final squared. And that's what we're trying to find, is the final velocity. So let's solve for it. V final is equal to, we'll multiply both sides by 2. You get 2 times the final kinetic energy divided by the mass. Take the square root. So let's plug in our values now. 2 times 1,180 joules divided by the mass, which is 15 kilograms. And you plug all that into your calculator, and you should get 12.5 meters per second. And that's how you solve this problem. Now, look, notice that I did it a little bit differently than the book. If you go and read the book's solution to this problem, they don't start with this. But this is a big deal. If you recognize a problem, say, hey, this problem, mechanical energy is conserved in this problem. The only force doing any work at all is either gravity or springs. Then you can say, my initial mechanical energy will be equal to my final. And then you just have to say, okay, where is my initial energy? Where is my final energy? How's it stored in my system? Plug in your, the equations for potential energy and for kinetic energy, and then you solve for the unknown. It's actually pretty easy. It's very similar to momentum. Remember when we started with P initial equals P final? Only this is easier because it's scalars. You don't have to worry about direction. It's all scalars. Any questions? That is all.